This is Bruce with Z Group Energy. It's March 25th, and if you're interested and have a minute or two, I'd like to talk to you briefly about variable geothermal reservoir flows and Z Group Energy's method of dealing with that particular issue. As you likely know, generation of electricity by geothermal methods is an exciting energy alternative, is cost competitive with other renewable sources, but is not without its own perplexing and I would say irritating issues. Geothermal fluid harvesting is always like taking one step forward and a half step back on a harvesting replenishment tightrope. Conventional two-pipe geothermal systems employing return wells for harvesting hot reservoir fluids balanced by injection wells for replenishment of reservoir levels, pressures, and flows, necessarily cope with variable reservoir temperatures, pressures, and permeable flows through misbehaved hot rock reservoirs. Of these three issues, variable temperature is usually the least significant issue, with variable pressure and flow holding number one and number two positions of concern. ZGE refers to these variations in temperature, pressure, and flow of hot fluid or steam as hiccups. Expensive, delicately balanced, finely tuned steam turbines can be damaged by feed flow variation in steam temperature, pressure, or flow. For these reasons, and I suppose a few more, geothermal power plant operators responsible for providing safe, reliable electricity to franchise service area customers do not want their systems getting the hiccups. Now, why does ZGE characterize conventional two-pipe geothermal systems as one step forward and a half step back? Well, an aquifer, as you may know, is an underground layer of permeable water-bearing rock comprising a connected system of void spaces like cracks, fissures, sometimes larger openings, all of which can hold water and through which water slowly flows. When an aquifer is discovered at depths sufficient to generate adequate heat, as you know, the deeper we go, the hotter it gets. Right, the center of the earth is thousands of degrees. So when you get deep enough to generate adequate heat and the rock strata is permeable enough to provide economically viable flows, the aquifer can be utilized as a geothermal reservoir from which heated fluid or steam is harvested via what is usually called a return well. Now, the good news is these hot underground reservoirs allow harvesting of heated fluid or steam for generation of electricity or for other uses. You can heat building and cook food and do all sorts of things with geothermal if it's not hot enough. But if it's good and hot, you can generate electricity with it. Now, the bad news is the rock strata may not be quite permeable enough to enable economically viable flows, in which case fracking can be used to create more cracks, to open existing cracks further, thereby increasing permeability and flow, and to prevent already open cracks and fissures from closing, which would reduce flows, wouldn't it? Now, the process of increasing rock permeability to increased harvesting flow rates has the unfortunate side effect of also increasing losses, at least some of the time. That is, flows away from the return well. Fluid pressure is equal in all directions away from a given point, which makes it difficult for plant technicians to direct pressurized underground flows toward the return well rather than away from the return well. This below-ground complexity sometimes results in overall diminishment of harvestable reservoir capacity, or it may create the hiccups we mentioned earlier. Now, can these problems be dealt with? Well, yes, of course they can. ZGE's patented sealed geothermal technology bypasses reservoir variability and corrosive brine issues in two major ways. The first is to store heated, dynamically homogenized, preferably supercritical fluids obtained from multiple heat sources above ground in the sealed, insulated ZGE exchange chamber. You can see in the sketch there the exchange chamber up on the top, and you can see heat cylinders going down into the ground. Now you only see 3 cylinders there, that particular drawing. If you're looking down, there's actually 7, but we only see 3 in section. And you see those cylinders extending down into hot rock. And you see the up and down arrows, blue arrows going down, that's cool water. Red arrows, that's heated water going up. Okay. Now, uh, so the first thing that we want to do is we want to store our heated water above ground in that nice exchange chamber. Okay. And we do that instead of utilizing the below ground reservoir, so that far below ground we have to regulate a very difficult to regulate open system of cracks and fissures that constantly demands replenishment. Now the second item, the second thing we have to accomplish is to harvest the underground heat, okay? Not the underground fluid. If you look at that picture, those heat cylinders going down are sealed. We're harvesting heat, not underground fluid. We do that by utilizing a system of sealed heat cylinders or wells, within each of which clean cool water is conductively heated, preferably to supercritical temperatures by surrounding hot rock, whether wet or dry, then convectively rather, delivered to the exchange chamber for mixing, storage, and discharge to a pressurized storage container, which I'm not showing in the drawing. But that exchange chamber discharges to a pressurized storage container for final mixing, additional storage, and final adjustment of temperature and pressure before any discharge is made to electric generating equipment. Now, sealed heat cylinder flows are non-partitioned convective flows, both injecting and harvesting within a single pipe. Temperature, pressure, and flow variation between the multiple heat cylinders are balanced within the exchange chamber, where clean heated water is stored, discharged, and replenished via a mixing container, also not shown in the sketch, where clean water and cooled condenser water are combined in a continuous closed cycle. So we have the cool incoming water coming into the exchange chamber on the bottom there on the right. You can see a blue arrow. And the exchange chamber, each heat cylinder is going to have a slightly different temperature, pressure, flow rate. They're not going to be the same. And it doesn't matter. They all go into the exchange chamber and the whole mix is balanced and homogenized in that chamber. So yes, some of the cylinders will produce more than others, some less. We don't care. Overall, you're going to get a nice homogeneous mixture, well balanced, okay? Now, this closed system drastically reduces water demand of the overall system, and the system redundancies built into it from the mixing chamber, the exchange chamber, the pressurized storage container, and so forth virtually eliminate any possibility of hiccups. Now, if you'd like to know more about sealed systems, supercritical geothermal, please visit our website at www.zgroupenergy.com. We'd love to hear from you. And incidentally, we'll be addressing additional issues regarding conventional two-pipe geothermal systems, issues such as water demand, corrosivity, toxicity, geographic restrictions to the boundaries of tectonic plate areas, and so forth, in coming videos. Okay, so if you're interested in any of that and would like to learn more, please stop on back. Thanks so much for visiting.